Just as we saw in the last couple of sections with combining resistors within a single circuit, it's also useful to look at combining multiple capacitors within a single circuit. So in this video, we're going to look at what happens when you combine capacitors both in series and in parallel. All right, so here we have three capacitors that are arranged in parallel. Just like we saw with resistors, the voltage from point A to point B is going to be the same. So your terminal voltage, or your voltage from point A to point B, that's going to equal the voltage that is produced across capacitor 1, and it's also going to equal the voltage which is generated across capacitor 2, equal to the voltage across capacitor 3, and so on. Now let's take a quick look at charge before we move on to the next slide. The terminal is able to produce a certain amount of charge Q on the capacitors within that circuit. Now that charge Q, the total charge Q, is going to be separated between charges Q1, Q2, and Q3, depending on what the capacitances are. So the total charge is just going to be Q1 plus Q2 plus Q3, so on. So in parallel, just like we saw with resistors, the voltage drops across each resistor is the same, so the voltage gained on each capacitor is the same when in parallel. And just like with resistors, the sum of all the currents equals the total current. Likewise here, the sum of all charges across each capacitor is going to equal the total charge produced by the terminal. So let's take a look at what would happen if we use the capacitor equation Q equals CV. We're going to take our equation Q is equal to Q1 plus Q2 plus Q3. Well, Q is equal to the equivalent capacitance times voltage, so we get Q is equal to equivalent capacitance times voltage. Then we do the same for each charge Q1, C1V plus C2V plus C3V. But this voltage is the same for each capacitor, so that divides out, and we see that the total capacitance in parallel is going to be the sum of each capacitor. Now remember that when we talked about resistors, this was the case in series. But no, adding up the capacitance will give you the total capacitance in parallel. I'll show you a summary of that in just a second. Let's look at series. Now, when talking about voltage, you have a certain amount of voltage here, then you're going to have a certain voltage drop across each resistor. Likewise, here in a series circuit, the total voltage available from the battery is going to be divided equally among the capacitors. So your terminal voltage is going to be V1 plus V2 plus V3, so on. But we saw with resistors that a current in a series circuit is the same through each resistor. Likewise, the charge produced by your terminal is going to produce equal amounts of charge on each capacitor. This has everything to do with the fact that currents are the same throughout the whole series circuit. Now if we do the same thing, we use the capacitance equation, Q equals CV, but we're going to use this form. We're going to add up the voltages, so let's solve for voltage. Voltage would be Q over C. So your terminal voltage would be Q over the equivalent capacitance, and then across each capacitor, Q over C1, Q over C2, and Q over C3. The Q's are the same, so if you divide out the Q's, you end up with adding up the inverses to give the inverse of the equivalent capacitance. Remember that for resistors, this was the rule for resistors in parallel, but for capacitors, this is the rule for capacitors in series. So in summary, in a series circuit, You add up all the voltages to give you the terminal voltage. All the currents are equal throughout the entire series circuit. To get the total resistance, you just add up the resistors. And to get the total capacitance, you use the inverse property. 1 over each capacitance, sum of that would be 1 over the total capacitance. Go to the other side with parallel. The voltages across each item in a circuit in parallel is going to be the same, whereas the current or the charge is going to be separated between each branch. So the total I1 plus I2 plus I3 is going to equal your total I, or Q1 plus Q2 plus Q3 equals the total charge of your circuit. And that goes over here as well. When you have resistors in parallel, you use the inverse property, 1 over each resistor, add them all up. That is equal to 1 over your equivalent resistance. But for capacitors, you just merely add them up. So this is a good summary here. Good to note all of these equations, this summary right here, to tell you the relationships within a circuit of capacitors, resistors, voltages, and currents.